don't even know if I can call them a database company, but I think of them as a database company, CoreLogics. And Dan has come all the way from Virginia just to speak with us today, so I hope you all make him feel very welcome.
Thanks. Fun fact, it took me longer to get from LaGuardia to here than it did to get from my house in Virginia to LaGuardia. So, I'm not good at coming up with talk titles, so it's Scalable Analytics on Dynamic Semi-Structured Data. And that doesn't sound like it means anything, but hopefully it'll make sense by the end. So I work for CoreLogics. So we're a full-stack SaaS observability company. So it's like your one-stop shop if you need observability that's not going to make you go broke as a company. And what I do specifically for CoreLogics is build our remote query system, which is basically a way for customers to store their raw observability data in a sort of lakehouse that gives them all the sort of analytics capabilities they want and need, but at a reasonable price because we can store everything. And oh, sorry, can you hear me? All right, yeah. So first, 3 observations about observability data. One is there's a lot of it, and there's more every day. This is why observability is so expensive, because we charge by the gigabyte, and there's lots and lots of gigabytes coming in 24/7. It's structured data, right? So it's 2024, we're all using structured logging and all that good stuff. So it's not just text strings of logs. It's basically arbitrary JSON that's coming in. And it changes a lot, right? So think about every time you're in your code base and you add a new log statement and add a new attribute and add the same attribute in multiple different places with different types. So it's constantly changing. There's constantly conflicts between the sort of data structure and the sort of inferred type that we get from it. So it's sort of a challenging problem to build a lake house on top, or a data lake with this sort of data. All right, so the interesting problem then is like, okay, so we know that the way to build a modern high-scale OLAP system is with columnar data, right? We want to store data in Parquet or whatever. But these columnar data doesn't mesh very well with like complex nested data structures, right? So it's columnar, right? It's hard to represent complex structure in there. So we're trying to solve this problem, and like the first thing we do, of course, is we go like, look, what's the prior art here, right? We can't be the first people who've come across this problem. So I'm going to talk about sort of 3 different approaches that are kind of out there in industry and academia first, and why we did something slightly different. All right. Oh, it's not like synced to the screen for some reason.
His slides are not up to date with the...
Yeah.
Oh, that's interesting.
Yeah, probably. If the Wi-Fi just...
There we go. All right, let me back up here. All right, now the clicker doesn't work. All right. So approach number 1, and like if there is a standard way to do this, this is the standard way to do it. It's called record shredding or Dremel encoding. So this was introduced in the Dremel paper from Google. Like they built a data lake that handled semi-structured data, and they had some their own sort of flavor of SQL where you could sort of work with structured data, and it was all very nice. And basically, the way this works is that you can take the leaf values. You can think about, you've got your JSON object, and at some point you've got a leaf value, which is just a scalar value. So you can sort of flatten that down, and you can take a bunch of those values, and you can save the leaf values at the same path in the same column. So you get a nice columnar value of scalar values. And then you can add a little bit of extra metadata that allows you to sort of reconstruct the nested structure. And so there's two specific pieces of metadata. So there's a repetition level and a definition level. So the repetition level or rep level basically tells you when you have something that repeats at multiple levels. So think of like an array of arrays. It basically tells you for each row in your column at which level it actually repeats at. So is it another element in the inner array, or is it the first element of the next array in the outer array? That was a bit of a mouthful, but and then definition levels basically tell you if you have a null value somewhere in your column, which level in the tree is it actually null at, right? Because if you have like a null value at a higher level in the tree, then all its subvalues are also implicitly null. So you need the definition level to sort of tell you at which level it's actually null. So this was stolen from the Dremel paper, and it's just sort of a demonstration of how the nested data structure sort of gets mapped into a columnar format, right? So every column, you've got just kind of your values stored as a regular array of values, and then each one has a repetition and a definition level associated with it. And that is sufficient to sort of reconstruct any arbitrarily complex nested data structure. And this is great. It works pretty well for if you have like a table with a fixed schema that happens to be a nested structure. You can do this pretty efficiently, and there's all sorts of cool things you can do in terms of how to like do query processing with this knowledge. But there are some. Let's see if the clicker's back. Nope. There are some problems with it from our standpoint, at least. So. As the name implies, you sort of shred the record. So to get the record back, it means you need to like sort of piece it back together. And while that's fine if you have a relatively static structure that's doesn't have too much complexity, if you have a really wide column table, like thousands of fields, it's extremely expensive actually to decode all these columns from your storage layer and sort of reassemble this nested structure. And so it ends up being extremely costly to read this data, especially if you need to read the entire original source object. But beyond just sort of the inefficiency of it, what it does is implicitly takes all the data that's stored together in a single chunk, and it sort of merges all the schemas together. So you can imagine if you have a lot of heterogeneous data, what you end up with is this sort of Frankenstein schema that is like extremely sparse, right? So you send it this nice, compact JSON object, and what you get back out is this like monstrosity that's got like 4,000 null fields, right? So that's not great, right? We want to like preserve that original structure. And just tracking the schema itself is a non-trivial problem in a huge distributed system where you're ingesting gigabytes upon gigabytes per second. And then, dealing with type conflicts, you can do it, right? So, we're sort of using the arrow format, which has union types. So you can always resolve type conflicts by lifting things into unions. But it adds a whole nother level of complexity that's just super annoying to deal with. So this is kind of a non-starter for our use case. But fortunately, things move forward. So we found a paper from 2014 about a system called Senu. And so this was really proposed to solve the sort of exact problem that we had, right? And the sort of key idea here is that you kind of have like a logical structure, so the logical schema of the data, but that doesn't need to match the actual physical representation. So what you can do is kind of have this logical schema, and you can partition it into logical and physical columns. And the physical columns get materialized into their own, storage layer, either, part of the tuple in a, row-oriented database, or into their own column in a columnar database. And so you can sort of gradually materialize these columns based off some, magic algorithm or something. And during query time, you sort of tracking which columns are physical and which are virtual. And basically anything that's not a physical column and materialized into its own column or field is just kind of stored in an efficient binary structure, so that it can be materialized on the fly at query time. So you can sort of bridge this sort of gap by like strategically materializing columns and then storing everything else in a sort of binary format and just kind of working with it on the fly. And they propose this thing, the schema analyzer, which basically is in charge of figuring out what to materialize. And once it makes a decision, like to materialize a new column, it'll go back and materialize it for the old data. So it's a really slick system, but it was sort of, the context of the paper was creating like a single node database, right? So your schema analyzer is kind of running on a single node and can go back and rewrite blocks of data incrementally as it changes the physical and the breakdown of physical and virtual columns. And so, the problem with this is just basically that, you take this and you scale it out to a system with, hundreds of nodes, and it's really hard to implement that schema analyzer. Like, it becomes a very wicked distributed systems problem, which we didn't feel like solving. All right, so fast forward to 2021, and another paper called JSON tiles. So this was from Thomas Newman's group in Munich, I think. So like anything you ever want to know about databases, Thomas Newman and his group has a paper on it. But this one was super interesting because it's the same conceptual idea as Senu, basically, right? You have evolving semi-structured data which may not conform to the same schema. You want to separate it into materialized columns, which are physically materialized in the on-disk representation, and the sort of virtual columns, which are all stored together in some binary format. But what their sort of contribution was kind of a novel way to figure out what to materialize and what not to materialize. And specifically in a way that sort of made that decision more local to an ingestion process. So it's like a way to sort of scale up the schema analyzer from Senu. And so I'm not going to really go into depth on the algorithm, but the gist is, and where the name JSON tiles come from, is that basically you take, as your data is coming in, you chunk it into what they call tiles. So that's like, say, 64,000 records. And then for each tile, you run FP growth, which is a pattern mining algorithm to find the frequent item sets, which would be basically the fields that tend to show up together in the same record. And then you take, once you have like 8 of these tiles, you start swapping records between the tiles until you get a better match. So, the details are, more complicated than that, but the basic gist is you take the data and you start you have a sort of process to swap it around until you co-locate the data that looks like each other in the same tile. So you get sort of an efficient allocation of your physical columns within each tile. And this can be a decision that you make sort of as a local decision on a specific chunk of data that you're ingesting, so you don't necessarily have to do this whole complex distributed system problem to like reach consensus on the exact schema. You can just sort of do it in a streaming incremental way. So very cool, but you know, as we sort of tried to like work on this, it's also has its own set of scalability problems. FP growth is not a super efficient algorithm, so it starts to get super expensive to run this algorithm at scale. So we said, like, let's take these academic papers and let's do like the dumb guy version of them, right? So this is the format that we call CX data, right? So you know, as a physical file format, it's just Parquet, right? So we didn't like invent our own file format or anything. And so we take the insight from Senu and JSON tiles that, okay, we want to sort of partially materialize these structured objects. We're not going to deal with super deeply nested stuff, right? We're going to only materialize scalar values and arrays of scalars, right? Once you start to get into, you know, arrays of objects of arrays, we're just going to chuck all that stuff into the sort of blob that contains the entire object, and we're going to materialize the simple stuff. And we're going to materialize based off a really dumb heuristic, right? We're going to take the data that we're ingesting as a chunk, and we're going to look at the top, you know, n least sparse columns, and we're going to say we're going to materialize those, and that is a local decision to this one chunk of data, and has no bearing on any other data that's ingested into the system. So it makes the ingestion process scale really well, because like as you're parsing this data and building up this, building up this schema, you already sort of know, you know, calculating how sparse a column is a trivial calculation. So this doesn't add a lot of, like overhead to the ingestion process above like creating the Parquet and doing all the encoding and writing it out to storage and stuff, and sort of gives you a lot of the benefits of these other systems. And then there's no actual coordination during query execution either, right? So we're basically, we can sort of infer the types that we need to know from the query itself and some other metadata, which I won't talk about here. We have a system that basically tracks type information of individual fields, like at the field level. And so with that, we can look at a query itself, sort of infer what schema we need to impose on it. And then from there, it's just like, okay, go read, when you're reading a file, either this column has a materialized column or it doesn't, and then if it doesn't, we go materialize it on the fly. So it's like the sort of simplest thing that could possibly work, but it works pretty well. So okay, so something that Senu and JSON tiles both have in common is you actually need to store the sort of non-materialized columns in some sort of efficient format, right? You can just like chuck the JSON string in a string column, but then when you need to materialize something on the fly, that's going to be super duper slow, right? Because parsing the JSON, all that stuff is going to be terrible when you're trying to scan many terabytes of data. So here's a little example of actually what this looks like, right? We have 4 objects, and we say, okay, our path AE there, or ADE, is sort of a complex nested object, so we're not going to fool with that. But we're going to materialize A, B, and AC, and then we're just going to store in this root D column, we're just going to store like the raw object itself. But we're not storing the raw JSON like this picture. We need an efficient binary format. So again, binary formats. What's the prior art here? Well, there's a lot of prior art, right? There's Postgres JSON-B. There's BSON, which they use in MongoDB, and now is its own like standalone specification. SQLite just added JSON-B support, and they have yet another JSON-B implementation. There's Amazon Ion, there's Message Pack, and there's probably 24 more. So I should have put the XKCD cartoon here about the 14 different standards. Maybe I'll give this talk again and that. But where I'm going with this is we invented our own. All right, so I'm not going to talk about all these specifically, but I'm going to talk a little bit about what JSON-B looks like and just sort of set the stage for why we did it slightly differently. It's actually very similar. So how Postgres JSON-B works is basically you have this JSON-B value, which kind of has two different parts, right? So it has an array of J entries, which is a fixed 4-byte data structure, and then you have all the variable length stuff kind of appended to the end of that. So each J entry has like a 4-byte header, the 4 most significant bits. So the top bit tells you basically what the bottom 28 bits mean, and then the next 3 most significant bits are a type, so they tell you, what sort of type this is. Is an object, an array, string, et cetera, et cetera. And then the bottom 28 bits are either a length, the length of the value, an offset into this var length section of the JSON-B value, or if it's a container type, an array or an object, the number of children it has. So the number of elements in the array or the number of key and value pairs in the object. So basically you get this nice cache-friendly fixed width structure that's easy to sort of iterate through and traverse. And you get random access because the reason why they do the length or the offset is because every, I think 32 J entries, they do an offset into the value, and then it's the next 31 values, I guess, contain the value length. So you never have to traverse more than 32 J entries to find the offset into the value buffer for a J entry. So this is great. It works great. Postgres is amazing, but it sort of has some features that are not fantastic for a columnar storage engine. So you can't really do one approach to this would be to just take something like this. We're going to take Postgres JSON-B, and we're going to throw our values as a JSON-B value into a binary column and call it a day. And that would work pretty well, but there are some issues with it. One is you're storing everything together, so you're not able to actually prune any I/O if you're trying to do materialization, right? Because you kind of have to read the whole column as a column chunk so that you can then sort of traverse through here. And it's fast to traverse through here and find the value that you want, but it's not, in a data lake architecture, like the sort of I/O is the dominating factor, right? So you're trying to eliminate I/O as much as you can. The TLDR is basically, you can tweak this a little bit to make a format that is sort of more well-suited to a columnar storage engine. And the small tweaks is basically you take these J entries and variable length values, and you separate those into different columns, and you actually split out the variable length values into 2 separate buffers, one specifically for keys and one for values. And you do that because the keys are repeated a lot, so you can get a lot of mileage out of dictionary encoding them in a lot of cases. But also because if you want to traverse this, say you want to find a particular path in this object, or find whether the object exists at all, the path exists at all, you can read just the keys and the J entries, and you can basically traverse the entire structure. So those sort of completely specify the structure. So you can do basic predicates like, does this key path exist or not, as without reading this value buffer at all, which is where like the bulk of the data lives. And you can also sort of rewrite certain sorts of predicates, like if you say, you have this path equals 1, you can sort of implicitly rewrite this as not equal null and is equal to 1. So you can basically like prune all the I/O for all the rows in which that path doesn't exist at all, and sort of prune a lot of I/O that way. So we call this thing JSON A or JSON arrow. Well, some of us call it JSONA, some of us call it JSON A. It's hotly debated, so we'll see. And yeah, so all the stuff I just said, separate the structure from the data so you can prune I/O more effectively. And yeah, so you can sort of tie everything together in that way, right? So we get the virtual versus physical column separation, and we have an efficient data structure that we can materialize the virtual columns in the event that we need to in a sort of efficient, cache-friendly way. And is that it? Oh yeah, okay. So one more slide for benefits. Yeah, you can extract values. It's actually faster to parse than if you're using, we use Rust. So, if you're parsing with 30 JSON value, it's about 40% faster to parse. There's no intermediate representation during the parsing. So like basically the incremental state, there's no like parse tree you have to create and then convert that into a value. You're basically building the structure as you're sort of processing tokens and the input string. So it's pretty fast, efficient. We can do basic predicates without reading the data at all. And I guess it's the same with JSON-B, but you can lose a lot of cycles trying to do things like string unescaping in JSON and things like that. So if you parse it and do all the unescaping when you store it and you have like the raw string value there, you can sort of save a lot of cycles. And if you want to do something like full text search across these, you can only read the values, right? Because you don't care about the structure at that point. You're basically saying, I want to search in all the fields, but the fields are nice compact structure for you to search through. And I think that is it. We are hiring, so if you're interested in database engineering, systems programming, stuff like that, let me know. Cool, and that is it. That's all my information. Thanks, everyone.
Just repeat the question when you get.
All right. Yeah.
And this is probably just like not being familiar with like the Senu work and all that.
Yeah.
But like if the decision for which columns to materialize is done on like a per chunk basis, and does that mean then that when like during query execution, like the each chunk might have a very different set of columns that it's like using the pre-materialized columnar file versus like materializing on the fly? And is it common in practice then that like querying each chunk across your entire data lake might all look very different?
Yes, so it does make things like partitioning, if you're trying to do a distributed query, a challenging problem, because you basically don't know when you're planning the query and you have to do the partitioning where the data is materialized and where it's not materialized, right? So you can like split the data into even-sized chunks, but then one partition may take significantly longer than another because because that happens to have that column happens to be virtual in that particular chunk.
Do you have any background process that looks through all the chunks and reorganizes them?
Yeah, sorry, I forgot to repeat your question. Yeah, so the question is there like a background process that kind of rewrites the data or does anything like that? And no. So it's basically, it's not currently feasible to do that because there's just a lot of data. So we're working on smarter ways to do the materialization, But right now, it's basically a one-time decision. Sort of, you make it at the time you ingest the data. What that means in practice is that we materialize very aggressively. But ideally, you get to a point where we can be a little bit smarter about it. Right. Yeah.
It's a really basic one. Like, how large are the Parquet files that you, like, as you're buffering and ingesting data, like, do you have a target size for the Parquet files, like rows, megabytes?
Yeah, so the question is there a target size? So right now, they basically between 50 and like 300 megabytes. So we basically write so like based off the SLA, we basically you're basically buffering enough data for the particular table, or you're just writing what you have when an SLA expires, and you need to write the data so that it's queryable. So for a very high volume table, that might be like 300 megabytes, but it can be 50 megabytes. So it's sort of driven by when the data has to be available to be queried more than anything else. And then that can get compacted into larger files. But the way we sort of treat it is like the unit of the sort of unit of scanning is the row group within the Parquet file. So even when we sort of compacted into larger Parquet files, from the query engine standpoint, those are like individual blocks of data that just kind of happen to live in the same file. And do you have a question?
Is JSON open source anymore? Or can we do more about it?
It is not, but it will be at a date that I cannot give you right now.
But you made this promise before, the last time I talked to you.
I did.
Oh.
Who invited you, Paul? Yeah, it is. We are planning on open sourcing it, but it is not open source yet. So, yeah.
In practice with customer workloads, how varied are the schemas that you see across chunks?
Yeah, the question is how varied are the schemas? Extremely varied. So, we sort of, right now, we kind of dump data into very big silos. So it's like all of your logs data go into a single table called logs, right? So this could be from 1,000 different systems, using different logging libraries and everything. So the schemas are extremely varied. And then we have systems and ingestion to help try and solve this problem. But every once in a while you get somebody who decides to make a UUID, a key in their object, right? And so all of a sudden you have, an object that's, a chunk that's got, 17 million columns or something like that. So we have ways of preventing that from blowing anything up, but it's a constant problem. All right, cool. All right, well, thanks everyone.